Hi, today's notes cover comparing distributions. Often in statistics, we will have two sets of data that we want to compare. If we were looking at experimental results between a control and a treatment group, or comparing two different years of data, etc., we often want to compare multiple sets of data. So any of the graphical representations, dot plots, histograms, side-by-side box plots, back-to-back stem and leaf plots, etc., can be used to compare two or more variables on center variability, clusters, gaps, outliers, and other features. Remember, variability is a fancy way of saying spread. So you can see there's two graphs right here. The first one is pulse rate before and after exercise, and the second one is the age of swimmers in the Olympics from 1984 and then from 2016. So in both those situations, we just like to compare what's happening between the two different groups. So what should your answer include? Well, if you don't have a graph of each set of data, you want to make a graph using all the the graphs that we have talked about, picking one that would be the easiest for that set of data. And then we want to mention the SOCs for each distribution. Shows shape, center, spread, and outliers and unusual points. We'd like to make a comparison statement at the end of the comparing distributions, where we're saying, like this group is more than this group, et cetera, et cetera. And you should always, when you're talking about the distributions, include the context. Okay. As you're writing up a comparison, you need to mention SOCs for each distribution, and you don't want to just list out SOCs, like make two columns and just 1, 2, 3, 4, 1, 2, 3, 4. You want to weave the descriptions together, okay? You want to say, like, the shape of the pulse rates before exercise is skewed to the right, as is the shape of the pulse rates for after exercise. You might say something like, there are no outliers in the pulse rates before exercise, and there's one high outlier in the pulse rates after exercise. So you want to weave them together in complete sentences. The comparison statement, you want to at least one comparison. And you can use adjectives like bigger, smaller, greater, less than, larger, more, etc. Okay. When you're doing numerical summaries, you always want to either compare the median of one graph to the median of the other, or the mean of one graph to the mean of the other. Okay. And you'd only do that if both graphs are symmetric and unimodal. Okay. Because that's when you use the mean. For the medians, if one graph is skewed and the other one is symmetric, you'd still want to mention the median for both. Okay. In fact, you're always safe mentioning the median as your measure of center comparison. Same for the spread. You want to use the same spread measurement for both graphs. And usually in statistics, we're going to use the range. Because oftentimes we don't have all the data. Like if you look at the pulse rate activity graph above, there's no way we could find, let's say, the standard deviation of that. Okay, we could use the interquartile range on those two, because we can see them in the box plots. Okay, but range is great to use as a comparison. Include numerical values if you have the actual data points. So if you can find the median, you should find it. Obviously, again, if we have like histograms, if you're looking at, we won't be able to find the median exactly. So use the actual data points only if you have them. Like in this graph down here, the swimmers' ages, you could find the median of both of those graphs by just counting dots. Okay, so when you have a chance to actually find a value easily, you should do that. And then claiming there are outliers, you better check, or it's always safe to say there are potential outliers. Okay, like on this graph right here, you might call those potential outliers. Don't ever call something an actual outlier unless you're 100% sure and you've done the calculation. On the AP test, if you call something an outlier then it isn't one, they will subtract points. But if you call something potential outliers and it isn't one, you're fine. So sometimes we want to make kind of vague statements so that we don't box ourselves into a corner. So here's an example with the swimmers. Okay? These are the age of swimmers in years and 2 Olympic years. Using the information in the graphs to the left, it says compare the ages of swimmers in the 2 Olympic years shown. Which year had older swimmers? So I already wrote this up a little bit. The median age of swimmers in 1984 was 18 and a half years. There are 14 swimmers, so the median would be between the 7th and 8th swimmers. So I just counted the dots, and there were 14 of them, which means the median's between the 7th and 8th. So the 7th swimmer is this red dot, and the 8th swimmer is this one, so it'd be between 18 and 19. That's how I got 18 and a half. The median ages of swimmers in 2016 was 22 years old, and there's actually 22 swimmers in 2016, so the median would be between the 11th and 12th swimmers. So I counted in 3, 4, 5, 6, 7, 8, 9, 10, 11, and there's 12. So their 11th and 12th are both 22, so the median would be 22. Okay, so the median age was 3.5 years older in 2016. Now, carefully looking at the graphs, though, you'll also see that there are 9 swimmers in 2016 that are older than every swimmer in 1984. So I'm talking about these guys right here. Those 9 swimmers are older than everybody in 1984. Also, there are 7 swimmers in 1984 that were younger than every swimmer in 2016. So based on all this information, I would conclude the ages of swimmers in 2016 were, in general, older than the ages of swimmers in 1984. Okay, and again, notice I say in general, based on this information. So we're saying, just a general comparison between the two groups, okay? Obviously, if you look carefully, this swimmer in 1984 was older than all of these swimmers in 2016. But in general, the 2016 swimmers are typically older than they were in 1984. Okay? Here's another graph. It says the box plots below represent data collected on the length of recorded tracks from the top 100 rap and top 100 heavy metal music charts. You can see where they've created 2 box plots. First question says, on average, which type of music has longer tracks? Give multiple justifications. So if you look, based on the box plots, the median length of the metal tracks was 4.8 minutes. Remember, this is the median, the line in the box plot, so that was 4.8. And the median length of the rap songs was 4 minutes. Okay, so the metal songs, the typical song was 0.8 minutes longer. Also based on the box plots, you'd see the top 50% of song track lengths for metal are longer than, I'll give you a circle here. Remember, this is the top 50% of the data, and that's longer than all of the songs in the rap category, okay? And additionally, if you look at over 25% of the rap songs are less than the metal song lengths. So I was talking about these right here. I know it's more than 25% because this is Q1, okay? So at least 25%, but there's just a little more space there until we hit the shortest metal song right here, okay? So I said based on this information, I would conclude that in general, metal track lengths are longer than rap track lengths. Track lengths. It's hard to say fast. The next question says, compare the significance of the track length of 4.4 minutes for the 2 music types. Well, 4.4 minutes is right here on the graph, and it happens to be the first quartile for metal, but the 3rd quartile for rap. So, for the metal track lengths, 4.4 minutes is the 25th percentile, or the first quartile, meaning that 25% of the tracks are shorter than 4.4 minutes, and 75% are longer. For the rap music, 4.4 is the 75th percentile, or the 3rd quartile, meaning 75% of the rap tracks are shorter than 4.4 minutes, and 25% are longer. So that's the type of questions they will ask you when you're comparing distributions. Okay, so you got to know your quartiles and know your box plots. And then this is the typical AP exam question, where they'll give you two graphs and say, compare the distributions of heights for men and women in inches in the histograms to the left. Now, this is the female graph, and you can see there's a little F right there, and then this is the male graph, and you can see a little M right there. Hard to see because they're small, okay? So, we said both the male and the female height distributions are unimodal symmetric. Okay, I think you can see that by looking at the picture. If I draw a smooth curve around it, they're both unimodal symmetric. And notice I mentioned both graphs. That's very important. Okay, you have to measure, or you have to mention socks for both distributions. So like shape has to happen for both. Remember, we're doing our socks. Then I said the women's heights are centered around the mean of approximately 65 inches tall, and the men's heights are centered around a mean, of approximately 71 inches tall. Okay, and how did I find those? Well, I know in a symmetric distribution that the mean is going to be in the middle. So I just made an estimate based on those numbers where I drew that line, okay? Then I said, so I mentioned shape and center. Now I should mention spread. So I said the range of each distribution is approximately the same. The range of women is about 20 inches, and you find that by looking on the graph between here and here. And then I said for the men it's about 21, and again you find that one by looking on the graph between somewhere around there to somewhere around there. Okay, actually it's, yeah, right there. And then I said there do not appear to be any outliers in either distribution. Okay, there's nothing there I see, but notice I said does not appear, just in case there are one. This I've been general. Then in general, the typical man seems to be slightly taller than the typical woman. Okay, and we see that by the median. It looks like the typical man's about 6 inches taller than the typical woman in this information. Okay, so we mentioned socks, we mentioned shape, center, spread, and outliers for both distributions. And we didn't just list them, we weaved a description together. And notice how they worded this question, compare the distributions. Whenever you see that, that's when we do the socks. Okay. Then we'll do this one more time. It says compare the distribution of pulse rates shown in the graph on the left for a sample of people before exercise and after. Okay, so again we're doing socks because they asked us about a distribution. So it says the distribution of pulse rates before and after exercise both appear to be skewed to the right. Okay, notice they both stretch way out to the right. Okay, I can look from the median. Okay, they stretch out much more to the right than they do to the left. Okay, the median pulse rate for before exercise is approximately 77. I got that using the median of the box plot, and then I used the same median of the second box plot and found that the N after exercise approximately 98 beats per minute. So in that sentence, I mentioned both spreads. I said there's one high outlier in the after exercise distribution, which is obviously right here on the graph, and none in the before exercise distribution. Then I said the range of pulse rates for before exercise is approximately 45 beats per minute, looking at the high and the low of the box plot. And then I said, including the outlier, the range of pulse rates after exercise is approximately 60 beats per minute. And instead of the range, I could have also mentioned the IQR on these. When they're skewed, remember IQR is a good measure of spread too, but range is totally fine, okay? Then I made just a general statement. In general, post-exercise pulse rates are typically higher than pre-exercise pulse rates. And I also mentioned that pulse rates after exercise were also significantly more variable than before exercise because the spread was so much more. Okay, so I hope that gives you a good idea of how to weave the comparison together and using socks.